All right, I mentioned earlier that I wanted to tell you a little bit about the bicarbonate buffer system. And I want to create a laboratory version of the bicarbonate buffer. I'll let you see it actually work. But let's look at the background here. So you know that your body has water in it. And hopefully you know that as your body's cells break down sugars, they produce carbon dioxide. And of course, we pretty much know just from elementary science courses that we exhale a good bit of that carbon dioxide. But when you put water and carbon dioxide together, the term is the carbon dioxide gets hydrolyzed, and it forms carbonic acid, H2CO3. Okay, so CO3 is carbonate. You should know that from your polyatomic ions. It's got a -2 charge, so 2 + 1 hydrogens to go with it to even it out. So carbonate becomes carbonic or carbonic. Structurally, carbonic acid should be something like this. All right. The carbon is in the middle of 3 oxygens. It's double bonded to one of them, single bonded to the other 2, and then those oxygens are in turn bonded to the hydrogens. Now, what does carbonic acid do as an acid? Well, of course, acids interact with water. Arrhenius said they dissolve in water and produce hydrogen ions, which then turn around and bond to the water to form hydronium. So we're going to take one of these 2 hydrogens over here and we're going to move it over onto the water with a positive charge so that we get hydronium. And what does that leave as our conjugate base? When I pull one positive hydrogen out of this, that leaves a hydrogen and it leaves a negative charge on all that's left. So here's our conjugate acid. Here's our conjugate base. This is carbonic acid. This is called bicarbonate. Okay? That's just one you've just got to know. Some people call it hydrogen carbonate. Vast majority call it bicarbonate. This is one of those cases where the bi does not mean 2 in any shape, form, or fashion. It is a shortened version of an old prefix of bis, B-I-S, and we'll not waste any more time talking about that. You just need to know what bicarbonate is. Okay, so in your blood, you are going to find carbonic acid because there's water in the blood. There's water in it everywhere in your body. And as cells produce carbon dioxide by respiration, you produce carbonic acid. Some of that carbonic acid ionizes and produces bicarbonate. So you end up with both of those things in your body fluids, in your blood in particular. You have the weak acid, carbonic acid, and you have its conjugate base, bicarbonate. And this combination creates a buffer. So let's first look at what if we just had carbonic acid. Now, I'm going to skip over some stuff and just cut straight to the molarity given in this example I'm looking at. And the molarity of this, pretty low, 2.7 times 10 to the -3rd. So if that was the initial concentration and there's none of this and there's none of this, okay, then the Ka for carbonic acid which is 4.3 times 10 to the minus 7. That would equal, alright, so 4.3 times 10 to the minus 7 would equal x squared over 2.7 times 10 to the minus 3. I know I just skipped some steps, but surely to goodness, as many of these as we've done, you can hang. Initially, this is this amount. Hydronium is at 0. Bicarbonate's at 0. This goes down by x. These two come up by x. So at equilibrium, we have this minus x over x for hydronium times x for bicarbonate, so x squared. But then, like we always do, this is really small, so this is going to be really small compared to what it's being subtracted from. So we would get here 4.3 times 10 to the minus 7th times 2.7 times 10 to the minus 3rd, and then we take the square root, and that gives us how many zeros is that? 1, 2, 3, 4. So 3.4 times 10 to the minus 5 for x. Now x is going to be representing hydronium, so if we take the negative logarithm of that, we get a pH of 4.47. pH equals 4.47. So that's what we would have. Excuse me. That's what we would get for just the carbonic acid. But now, let's take another step with this. This particular problem shows that in our bloodstream, even though the carbonic acid may be, go ahead and finish writing the equation out here. What was it? 2.7 times 10 to the minus 3. The bicarbonate concentration that's also there is 0.028. So again, common ion effect. With some of this already there, according to Le Chatelier's principle, more of this over here drives equilibrium this way. So this is not going to ionize as much. It's not going to make as many of these because there are already some there. That means it's not going to make as much hydronium. That means the pH is not going to go this low. Alright, so we're going to subtract x. We're going to add x. We're going to add x. So that we're going to end up with 2.7 times 10 to the minus 3 minus x. X of hydronium, 0.028 plus x of bicarbonate. So this time, we say that 4.3 times 10 to the minus 7 equals 0.028 plus x times x over 2.7 times 10 to the minus 3 minus x. And our little technique to simplify this, anywhere we add x or subtract x, we'll just ignore it because it's going to be insignificant compared to those amounts that it's being subtracted from. So that's going to set us up for 4.3 times 10 to the 7 minus. We're going to multiply by this down here to cancel it out on this side. So that's going to be times 2.7 times 10 to the 3 minus by the way, this is not 0.001. You know that 2.7 times 4.3 does not give you a dead on the nose 1. There's more out there that you can't see. Now, how do you find it? Well, let's put this thing into scientific notation mode, which says SCI above the 5. So we're going to do a shift or a second function SCI. If I can get this out from under the glare of the light, that's 1.161 times 10 to the minus 9. All right, so this times this equals this, which equals 0.028 times x. So we need to divide by 0.028 to isolate the x. So we need to take this number over here and divide it by 0.028. That gives us x being equal to 4.146, blah, 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 times 10 to the negative 8th. What did x represent? It's the hydronium ion concentration. So let's get to get the pH, we take the negative of the logarithm of this number. So let's get the logarithm first. And now we want the negative of that. So what's the negative of negative 7.38? Well, yes, it's positive 7.38. And that, you can see, is a good bit higher than 4.47. The bicarbonate that's already there keeps the carbonic acid from ionizing as much. And by the way, 7.38 is right there in the normal range for blood. pH of blood needs to stay right around 7.35, 7.4, somewhere right around in there. Okay? So that is a very plausible pH for blood. Now, one last thing about this I had mentioned right here. You have both of these compounds here. If, let's say, hydrochloric acid, which is produced by your stomach, it's stomach acid. If you were to have an ulcer, and that hydrochloric acid were to get into your bloodstream from that ulcer, hydrochloric acid is a strong acid. That would make pH go way down, and you would be in big trouble. But because there's bicarbonate in your bloodstream, it will give its proton to that, which forms carbonic acid and chloride. And the chloride will probably associate itself with a sodium ion or a potassium ion. But anyway, what have we done? We've taken this strong acid that would make a major drop in pH, and we have converted it into a weak acid that will only create a small drop in pH. Okay? So, that's how buffers work. You know, we could put a base in and it would react with the carbonic acid and produce bicarbonate, which is a weak conjugate base. So we can turn a strong base into a weak base. We can turn a strong acid into a weak acid. And that's how these buffers protect us. They're your first line of defense against major changes in body fluid pH. And major changes in body fluid pH are very bad. Okay, so that's it for a little extra look at the bicarbonate buffer.